Very good afternoon. Uh, uh, I would like to extend my heartfelt thanks to Anjanee Kumar sir for accepting our invitation to be speaker for this Atal FLB program. Your expertise in the topic of advanced control and optimization strategies for modern electric vehicle powertrains. So uh, we are thrilled to have you as a speaker in this program. So I hope that our this session will enhance the knowledge of the participants. So I request our student Aswini Jha for giving the brief introduction on our speaker. Yeah.
Thank you so much, sir. Am I audible and visible?
Yes. Yes, madam. Yeah.
Okay. Okay. So first of all, this everyone is enjoying the whole FDP as it is going on. I too am enjoying as I am a very big car enthusiast and I love watching cars. First of all, good evening to everyone. And it gives me immense pleasure to introduce our distinguished expert for this session on advanced control and optimization strategies for modern electric vehicle powertrains. And we are honored to have with us Dr. Anjanee sir, who is currently serving as assistant professor in the NSUT uh, New Delhi, the esteemed university we all dream of. And Dr. Mishra is an accomplished academic and researcher with expertise in power electronics, electric drives, renewable energy systems, and advanced control strategies. His research particularly focuses on electric vehicles, where he has worked extensively on intelligent energy management, converter design, and optimization techniques to enhance the efficiency and sustainability of modern EV powertrains. He has contributed more than 80 publications in reputed international journals and conferences addressing critical areas such as battery supercapacitor hybrid energy systems, solar PV powered charging solutions, high gain bidirectional DC-DC converters, and control of BLDC motor drives for electric mobility. In addition to his impactful research, Dr. Mishra is deeply committed to teaching and mentoring. Through his role in NSUT, he has guided and inspired many young engineers and researchers. With his strong background and extensive contribution, Dr. Mishra is uniquely positioned to provide us with valuable insights today in this session. And so please join me in extending a very warm welcome to Dr. Anjanee Kumar Mishra. Sir, please take the stage. The stage is yours. Please guide us.
Okay. So thank you, Professor Jatin and Professor Akash for providing this opportunity to speak with you all. And also thanks to Aswini for this wonderful introduction of myself. So I am just going to share my screen and we'll start and discuss something about the electric vehicles and the optimization techniques for that one. So So is it visible, sir, Professor?
Yes, sir. Yes, sir. It's perfectly
Yeah.
visible, sir. Yes, sir.
Okay.
Yeah.
So good ev- good evening to all. Myself, Dr. Anjanee Mishra, working as an assistant professor at NSUT New Delhi. So the today topic of my presentation, and we will discuss about the advanced control and optimization strategies for modern electric vehicle powertrains. So in this coming slides or lecture, we will discuss about how we could able to optimize the efficiency and the compactness of EV, how and what are the conditions to hybridize the different energy sources to make an efficient powertrain, and also the selection of different motor drive techniques or motor drive for the EV depending upon their load capacity and depending upon their energy sources. So, before coming to the more technical in depth of the electric vehicle, let us discuss what is electric mobility. So, in simple words, if we want to define what is electric vehicle or electric mobility, vehicles propelled by an electric motor in which the electric current is supplied by the battery storage system. Whether we will discuss, apart from the battery, there could be some other energy sources, but in approximately or in the fundamentally, if you want to define the electric mobility or electric vehicle, it means there is a battery and there is a motor inside the vehicle. So that vehicle propelled by electric motor and the supplied power by the battery is called the electric mobility. So the basic concept of electric vehicle is to just replace the IC engines that is in the conventional motor vehicles to the electric motors. Electric motors could be the special machines like BIDC, busless DC motor, PMSM, or the conventional like the induction motor. So there are different components are inside the electric vehicle, but somehow we can say that we can conclude or we can conceptualize that there are some key elements that should be in the electric vehicle. That should be like DC-DC converter, high voltage DC-DC converter, low voltage DC-DC converter. Like the high voltage DC-DC converter is used to take the power or the voltage up to the rating of 400 to 700 volt and to convert it into the lower voltage to supply the auxiliary loads or the different parts of the electric vehicle. So it is one of the key component of the electric vehicle. The another one could be the battery management system. BMS is very important one because we all know that the battery management is one of the very key concept to optimize or effective performance of the electric vehicle, so that there could be no burning or blasting of the battery could be. So battery management system, it can be done by the two types. One is by just taking the current or voltage or some electrical parameters from the battery, and the other one is to also taking care of the mechanical or the thermal parameters. So a complete battery management system is having both the electrical and mechanical or the thermal management system. Okay, so the thermal management and the electrical management could be the complete battery management system that should be in the electric vehicle. And the other is the traction inverter. No doubt, to drive the motor, we always need an inverter or the converter. So in the case of the propulsion, this converter, that is the three-phase voltage source inverter or H-bridge converter, you can say anything, that is required in the propulsion mode to drive the motor. On the other side, if there would be some regenerative operation will be there, then we also need to a converter operation. That means AC to DC conversion is also required in that case. So this traction inverter is normally you can say is the traction converter, not the traction inverter, because in the propulsion mode it is acting like an inverter. In the regenerative mode, it will act like a converter. The another integral part of the EV is the onboard charging system. We will discuss later the different charging schemes like onboard or board charging schemes. So onboard charging schemes in which the AC from the grid, we are taking AC from the grid 95 to 265 volt AC and convert to a DC required for the battery charging that lies inside the vehicle. So these are the some key elements of the electric vehicles like DC-DC converter, battery management system, inverter converter set, different type of DC-DC converters. The DC-DC converters could be isolated, non-isolated, bridgeless. So there could be a lot of options are there. So I am not going to the deep into the historical development of electric vehicle. We all know that all these things that is it started long before 1769, but in really the first generation of EV is comes into the action in 1990. And after the development of like power electronics switches like IGBT in 1984 and transistor and HCR, it could be more easy to optimize or to make the electric vehicle more effective as compared to the conventional or IC based or diesel based conventional vehicles. So why electric vehicle? Why are we are talking so much about the electric vehicle? What are the advantages of electric vehicle? So there are a lot of advantages of electric vehicle like environmental or maintenance. So apart from this, it is also very cost effective. If we talk about the cost per kilometer, the electric vehicle cost would be somehow very effective as compared to the petrol-based, diesel-based, or the CNG-based vehicles. If we talk about the petrol, so here I am considering the petrol is 80 rupees per kilometer, but now it is more than the 93 or 94 rupees. Okay. So if we talk about the petrol-based vehicle, the per kilometer cost is nearly about the 5 rupees. But in the case of electric vehicle, we can see that it is reduced drastically up to 0.75 rupees per kilometer. So there is a huge saving of cost. Like in the monthly cost, if you compare the monthly cost, it is around 7,500 rupees. But in the case of electric vehicle, it is just nearly 1,125 rupees. If you compare petrol-based vehicle. On the other side, if you compare with the diesel vehicle, CNG vehicle, even though it is very cost effective, so there is a reason to switch to the electric vehicle and to leave the diesel based or the CNG or the petrol based vehicles. So apart from this cost effectiveness, these are the some advantages of electric vehicles, like no fuel, no emission, like if with renewable energy for charging, carbon footprint shrinks dramatically, cheaper to run, as we already discussed, wide range of speed. So if you use the motor like PMSM or the synchronous reluctance motor or the switch reluctance motor, you have a range of speed. You have a scope to varying the torque speed characteristic of that particular motor, and you can get the different modes of operation even in the propulsion mode very effectively. Okay. So like in the new Tesla car, if you take the example of Tesla electric car model, it runs at a speed of more than 300 miles per charge. So it is very something to catchy that even at a single charge, you can have the more than 300 miles per charge. Volkswagen also similarly promised a speed of 400 miles per charge for its next launch, and these numbers will improve with time, no doubt. The another is the health benefit due to the environmental and all these things. There is a better air quality will lead to the less health problem. So these are the some advantages of using electric vehicle and switching to the electric vehicle, leaving the conventional vehicles. And the most catchy advantages are environmental one and the cost effectiveness, required less maintenance. All of these are having the characteristic of electric vehicle. It is also the quieter as compared to the IC-based vehicles, cheaper to maintain. However, apart from having all these advantages, we must also talk about the limitations of electric vehicle, and we should have to focus. We all are researchers. We are continuously researching on the electric vehicle and to optimize or to make it more effective. So these are some pitfalls of the electric vehicles, and we should have been considered in our research to overcome these limitations. Like the range of electric vehicle is still a challenge. High cost due to battery storage system. Battery need to be charged, which takes larger time. Battery disposal needs to carefully manage. Like if we take the example of lithium-ion battery, so no doubt it is very compact as compared to the lead-acid battery. But having said that, lithium-ion batteries also need a very effective battery management system, because if you compare with the lead-acid battery, having the single unit of lead-acid battery is normally of 12 volt. Lithium-ion batteries of single unit is maximum of 4 volt to 5 volt. So if you want 48 volt of battery, you need a 12 unit of lithium-ion battery to connect into the series. And if you connect these lithium-ion batteries into the series, that there must be a voltage balancing technique that should be in your system for effective operation. Okay, so apart from having the compactness of lithium-ion battery, you need a very effective battery management system for lithium-ion battery. So we can say that as compared to the lead-acid battery, in the lithium-ion battery-based electric vehicles, you should having the more careful about the management system, like the battery management system and the thermal management system. Okay. So depending upon the energy sources, like hybridization of energy sources, we can broadly classify the electric vehicle into three parts. The first one is the pure battery electric vehicle, BEV. The second one is the hybrid electric vehicles. and the third one is the plug-in hybrid electric vehicles. So in the hybrid electric vehicle, there is a further classification of fuel cell and battery hybrid electric vehicle. The another one is the diesel IC or the gasoline IC engine based and battery HEVs hybrid electric vehicle. Whereas in the third, plug-in hybrid electric vehicle, you can classify parallel plug-in hybrid electric vehicle, series hybrid electric vehicle. There could be number of combinations are there, like parallel, series, series parallel, parallel series. So depending upon your design, you could be able to define the plug-in hybrid electric vehicle or classify the plug-in hybrid electric vehicle into different classes. Okay, and each of having their own advantages and limitations. So like we discuss about the main fundamental of the battery electric vehicle first. So in the battery electric vehicle, only battery is the source of energy to drive the vehicle. So there is no concept of series or parallel or hybridization is there. So battery electric vehicle is having the battery is the only source. So there could be two possibility to charge the battery inside the vehicle. One, by just swapping out the battery by the on the vehicle into the vehicle, or the second one is by plug-in charging. Therefore, this battery electric vehicle is also called the plug-in electric vehicle. So this one is also called the plug-in electric vehicle. So by regenerative braking, you could be able to charge the battery, or by swapping off the battery, or just onboard charging, you can able to charge the battery. So there are a number of methods could be there. So this battery electric vehicle, in which battery is the only source of energy, you can also call it plug-in electric vehicle. So you can see in this basic diagram of battery electric vehicle, there is a utility grid of 120 or 240 volt supply, and there is a AC/DC converter which is also called the, you can say, the rectifier, and this PFC converter and AC/DC converter. So there could be two possibility of in this configuration. Either you can directly corrected the power factor by using just only the AC/DC converter, or by just introducing one more converter like the DC/DC boost or buck to get the power quality, to overcome the power quality issues at the grid side, and non-isolated or isolated DC/DC converter. So in the case of regenerate, if you want to charge your battery in the regenerative operation, then you need to a bidirectional isolated or the non-isolated DC/DC converter. Okay, so here is the bidirectional DC/DC converter is there. So in the regenerative operation, this energy coming from the electric motor would come to charge the battery through this bidirectional DC/DC converter. So this bidirectional DC/DC converter and this non-isolated and isolated DC converter could be the high gain or low gain, or any number of, depending on your configuration or depending upon your requirement, you can able to replace these two converters. So hybrid electric vehicle. The second class is the hybrid electric vehicles. So hybrid electric vehicles basically combine the concept of IC-based engine and the electric propulsion system for better fuel economy. Because reliability is no doubt one of the major challenge of the electric vehicle, and to make it more reliable, the IC engine could be the one of the best option to integrate with the battery or some other sources to make the hybrid electric vehicle, in which the IC based engine is the primary source, or the battery operated propulsion system is the second one, or depending on you. Powered by both engine and motor, battery is charged internally through the engine, or either through the regenerative or through the charging one. So there are different configurations in this one: series, parallel, parallel, series, parallel, parallel, series, series. So there could be number of configurations are there. So it has also the same advantage like less fuel consumption, lower exhaust system by using the two sources. So HEV can be categorized into two main groups: fuel cell. So you can integrate a fuel cell with the battery, or gasoline and the battery-based HEVs. However, apart from this two, there could be some supercapacitor plus battery, or fuel cell plus supercapacitor-based EV, gasoline plus supercapacitor plus solar-based EV. So there could be a number of possibilities. So in fundamentally, if someone wants you to define what exactly is the hybrid electric vehicle, so in the simple words, a hybrid vehicle refers to a vehicle with at least two sources of power. So there must be two sources of power. And a hybrid electric vehicle indicates that one source of the power is provided by electric motor. So any vehicle is hybrid electric vehicle or electric vehicle there should be one source of power is provided by electric motor. There must be one power source is provided by the electric motor. On the other side, the other sources of motive power or the propulsion power can become from a number of different technologies, but is typically provided by an IC engine designed to run on either gasoline or diesel fuel. And that is called the hybrid electric vehicle. So that is the basic fundamental definition of hybrid electric vehicle. What are the different types of electric vehicles? Similarly, we have already discussed like gasoline, IC engine and battery. There could be another possibility of diesel IC plus battery, battery plus fuel cell, battery and supercapacitor. Basically, this supercapacitor is also called the ultra capacitor. So supercapacitor or the ultra capacitor is just similar to a simple capacitor, having a difference that there is a semi-permeable membrane in between the two plates, which enhance or increase the retaining power of charges of this capacitor. There is no much difference between the simple capacitor and the super or the ultra capacitor, but is having some manufacturing difference which make it more having the more retaining power as compared to the normal capacitor. It has a very beautiful, you can say, property, supercapacitor, that it can be charged up to the 0 volt. So if you connect a supercapacitor of 48 volt to your battery, your electric vehicle, so you have the flexibility to charge or discharge your supercapacitor from 0 to 48 volt. There would be no much effect on the life of this capacitor, supercapacitor. So you can discharge the supercapacitor or ultra capacitor up to the 0 volt, but not in the case of the battery, not in the case of the fuel cell. Okay, so and another advantage of using supercapacitor or ultra capacitor in electric vehicle, it enhances the dynamic performance. It is a property of quick charge and quick discharge. Quick charge and quick discharge. So in the coming slides, we will discuss why we need this type of sources along with the battery or the fuel cell in the electric vehicle. So another possibility could be the battery and flywheel, battery and battery hybrids, both batteries, two sources of batteries. Okay. So if we see the configuration of layout of gasoline and the battery centered HEV, you can see a gasoline engine, IC based engine, is directly connected to the torque coupler, and in parallel a battery pack, a powertrain, is connected to the torque coupler. So it is basically the parallel hybrid electric vehicle. It is the configuration of parallel hybrid electric vehicle. Both the IC based system and the battery source powertrain supply power or the torque to the wheels of the vehicle. So it is the parallel system. And if you integrate one more source like fuel cell or supercapacitor along with the battery and the IC based engine or some, like, there is a probability of having the different number of sources in your electric vehicle. So here in this diagram, a fuel cell, a supercapacitor and battery are connected to make the system hybrid. Okay. So in the fuel cell, we need a unidirectional DC-DC converter. There is no need of having the bidirectional DC-DC converter. However, with the supercapacitor and battery, there is a bidirectional power flow is there. So we always need a bidirectional DC-DC converter. However, there is a possibility that you can use the different high gain or the isolated or the non-isolated or the different bidirectional converters along with the supercapacitor and the battery. Like here I want to discuss, like with the supercapacitor, it is always preferred to use high gain converters. Okay, because the supercapacitor is of voltage of 12 to 18 or 24 volt. So we always need to match with the DC link capacitor. Always recommended to use high gain DC-DC converter. So there is a huge scope with the supercapacitor integration in the electric vehicle on the DC-DC converter side along with the energy management system. Okay. Similarly, with the battery, there is a use of bidirectional DC-DC converter because in the regenerative operation, you have to charge the supercapacitor or battery. And it depends on you whether you want to charge first the supercapacitor or the battery. But it always prefers, in the discharging case, supercapacitor would be the first source of energy. And in the charging case also, the supercapacitor would be the first source of energy. So there is a number of possibilities if you integrate two energy sources with the in the electric vehicle or hybridize two energy sources for the electric vehicle. There is a number of possibilities of power flow. Like by taking this example, if you take the powertrain one, so there could be one possibility that powertrain one alone delivers power to the motor. Okay. The another possibility, powertrain two delivers power to the load. Both powertrain 1 and 2 power to the load. Powertrain 2 obtains power from the. There is another possibility that powertrain 2 receives power from the powertrain 1, and also the energy coming from the powertrain 1 would run the load. So there are a number of possibilities are there if you hybridize two energy or the three energy sources. So there is a huge scope of research in such electric vehicles, like the energy management system, battery management system, uh, converters that could be able to bidirectional or the unidirectional characteristic for the battery or the supercapacitors, or with along with the other, like you can also use the renewable system like solar or wind. Okay, so here is a normal load profile. Okay, like load power requirement for the electric vehicle. You can see there is a random power requirement is there. So this first figure shows or demonstrate the power required during the overall driving cycle of electric vehicle. It is of a random nature. So to make the electric vehicle effective, particularly in the running case in the propulsion mode, there could be a very serious, you can say, the selection of the power sources to make it optimize the performance of the electric vehicle. Like if you divide this load profile, required load power requirement into two graphs, the first one is the average power. You need a smooth source of energy that is having the smooth power supply during the steady state, and there is this type of power supply during the transient, or you say dynamic, or in any other driving cycle. And in that case, supercapacitor of like sources are very effective. Like for this type of power, you can use the fuel cell or battery that provides the constant power throughout the driving cycle. And for this type of nature of load profile, the supercapacitor could be one of the best candidate. Okay, so it's always prefer for the for the transient cases, for the starting cases, for the accelerate cases, or even in the regenerative cases, supercapacitor would be charge or discharge first. So supercapacitor would be very effectively take care of this type of load profile. And for this steady state operation, battery or fuel cell would be one of the best options. So if you combine the battery or fuel cell with the supercapacitor, that could be very much effective in your electric vehicle for overall performance, particularly in the running case, in the driving case. So these are the some configurations of hybrid electric vehicle. Like you can see the first figure in the series hybrid electric vehicle, this IC engine is connected to the electrical generator and is then connected to the battery. And this battery and electric generator based IC supply power to the motor. And this motor is connected to the load coupler, or you can say wheel, through a gear. Okay, so this is the series connection. Means battery and this IC based system using generator is supplying power at a time. Okay, so it's depend on you whether you want to take from this one battery or you take from the IC. But there is an additional motor, this generator set is required in the series hybrid electric vehicle. On the other side, you can see in the parallel hybrid electric vehicle, there is no need of this electrical generator. Just this IC engine is directly coupled with the coupled to the wheel through this gearbox. So there is a reduction of one more component like the electrical generator, which make it more compact and efficient. And there is another series parallel or parallel series, so number of connections could be there possible. So like if you take an example of series hybrid system, where both the IC based system and the battery or the fuel cell system are connected in series. So this fuel tank and IC based system generate an electricity and which gives to the power converter or electric motor. So battery and both these giving power to the electric motor to run the electric vehicle. So the advantage of having this series connection, there is a mechanical decoupling between the IC engine and the drive wheels, allows the IC engine operating at its very narrow optimal region. Nearly ideal torque speed characteristic of electric motor make multi-gear transmission unnecessary. Okay. On the other side, it is also having some limitations, like the energy is converted twice. Okay, you can see there is a need of electrical generator with the IC. So the energy is converted twice, mechanical to electrical means IC to electric generator and then to mechanical at the wheel side. And this reduces the overall efficiency of system. So apart from having these two advantages, it is also having this disadvantage or limitation, you can say. The another limitations could be the two electric machines are needed. One is generator and one is propulsion motor. And a big traction motor is required because it is the only torque source of the driven wheels. Okay, so these are the some limitations of the series. Likewise, parallel is also having some advantages like both engine and electric motor directly supply torques to the driven wheels and no energy from the conversion occurs. Hence, energy loss is less. The another one, no doubt, compactness of the system. But on the other side, the limitation is having like mechanical coupling between the engines and the driven wheels. Thus, the engine operating points cannot be fixed in a narrow speed range. Okay, so it is one of the biggest limitation of having parallel hybrid system in your EV. The another, the mechanical configuration and the control strategy are complex compared to the series hybrid system. So the control complexity or the designing of the control for the hybrid, like parallel hybrid system, is somehow difficult as compared to the series hybrid system. So these are the some limitations. So depending on your application and depending on your target application, you can choose a series hybrid system or a parallel hybrid system. And there another is the series and parallel hybrid system. So in this series parallel hybrid system, the configuration incorporates the feature of both series and parallel. However, this configuration needs an additional electrical machine and a planetary gear unit, making the control more complex as compared to the series and the parallel one. So it is also having the advantage, like having advantage of both series one and parallel one. But along with that, the control complexity is little bit higher, okay, as compared to the series one or the parallel one. So these are the some power flow control in the EV. Like in the series one, the power coming from through generator set to the converter and battery to the motor to the wheels of the electric vehicle. So these are the some possible, you can say, the power flow into the series hybrid electric vehicles. Similarly, in the parallel one also, either the power coming to the wheels from the battery to the power converter to the motor, or the IC based engine to the generator to the motor, or in the normal driving, it is coming from battery to the motor. In the braking or in the, so in both the cases there are possible four modes are there. So it is very simple to understand for the series or parallel power flow in the series or parallel series or series parallel combinations of hybrid electric vehicles. In the series parallel, a similar action is happening. So up to this, we have discussed about the types of electric vehicles depending upon the combination of energy sources. Okay, either series, either parallel or parallel series or series parallel. There is another possibility to categorize the electric or classify the electric vehicle on the basis of load capacity. Okay, so depending upon the load capacity, you can define the electric vehicle like the light electric vehicle or the heavy electric vehicle. This light electric vehicle is also somewhere written like light duty electric vehicle or heavy duty electric vehicle. So in the class of light electric vehicle, the examples are e-rickshaw, e-bike, e-cycle, or in the heavy duty electric vehicles, e-cars, trucks, bus are coming. Okay, so you can define on depending upon the load capacity. So broadly, there are two classifications are there. First one basis on the energy source rate, and the second one is basis on the load capacity for the electric vehicles. So what is light electric vehicle or the light duty electric vehicle? So the light electric vehicles or LEVs are low voltage or low speed battery electric vehicles, namely e-rickshaw, e-bike, cycle, or stake boards, which have a weight less than 100 kg. So if you broadly classify the light electric vehicle or the heavy electric vehicle, so the vehicle having the weight less than 100 kg, this comes into the LEV class, or the vehicles that is having the weight more than 100 kg would come into the class of heavy electric vehicle. Okay. However, there are other parameters that could be able to classify these two vehicles, type of vehicles. So in light electric vehicles, there is inside two classifications are there, depending upon the power range and voltage class. So if you see the table one, observe the table one, low power light electric vehicle is the vehicle having power up to 10 kilowatt. On the other side, there is a high power light electric vehicles that is having the power range 10 to 30 kilowatt. So if you have the vehicle having the weight 30 kilowatt, that is coming into the high power light electric vehicle. And if you having the vehicle having weight less than 10 kilowatt, it's come into the low power light electric vehicle. So there is a range of 1 kilowatt to 30 kilowatt for the light electric vehicle. Inside that one, there is a further classification for the low power and the high power light electric vehicle. If you talk about the voltage range for the low power light electric vehicle, it is from 24 volt to 72 volt. And for the high power light electric vehicle, it is from 48 volt to 144 volt. For low power light electric vehicle is prefer for the short distance, and high power for the off highways electric vehicle short distance, even though for the short distance but the highway. Okay. And the speed for the low power light electric vehicle is less than 30 km per hour. And for the high power light electric vehicle, it should be greater than 30 km per hour. And the motor power, if you want to use a motor for your low power light electric vehicle, you can select the motor having the power less than 750. That also called the fractional watt motors, less than 750 watt, 500 watt or 300 watt. But for the high power light electric vehicle, the motor having power should be greater than the 750 watt. So these are the some parameters on which we can select or we can define the low power light electric vehicle and the high power light electric vehicle. But if we talk about the difference between the light electric vehicle and heavy duty electric vehicle, then the weight for the light electric vehicle is less than 100 kg, and for the heavy it should be greater than the 100 kg. And the power range for the light electric vehicle is 1 to 30 kilowatt. So if you having a electric vehicle which weight is less than 30 kilowatt, it means you are having a light electric vehicle. Okay, but if your vehicle weight is more than 30 kilowatt, then it's comes into the heavy duty electric vehicle. Okay, and battery voltage for light electric vehicle is 24 to 72, and for the heavy duty or the heavy electric vehicle is 230 to 900 volt. So these are the parameters by which you can able to define the difference between the light electric vehicle and the heavy duty cycle electric vehicle. It is very important to know these parameters, because depending on these parameters, you could be able to select your types of DC-DC converters or the types of motor or management system. Like, so you should know your electric vehicle is a light electric vehicle or a heavy duty electric vehicle, or in which electric vehicle you are going to work, and what are the different ranges for that electric vehicle. So apart from all these things, the types of electric vehicles, if you want to optimize or to make your electric vehicle effective, the charging scheme is also one of the key parameter. Okay, so there is a definition or there is a categorization of electric vehicle charging system also for different light electric vehicles, for the high duty or heavy duty electric vehicles, So if you want, also on the, depending upon if you want to charge your system fastly, or if you want to charge your vehicle whole night, overnight, okay. So depending upon that, you also need to select the charging scheme. So if you broadly define the EV charging scheme, that can be defined into, classified into, or broadly classified into two parts. The first one is the onboard charging, and the second one is the offboard charging. So onboard charging scheme is also called the slow charging or overnight is charging. On the other side, the offboard charging is called the fast charging. So there is a different level of chargings. So like level 1 and level 2 are coming to the onboard charging. On the other side, level 3 and sometimes level 4, that is also called ultra fast, or somewhere written DC fast charging, is come into the off-board charging system. So in the on-board charging scheme, most of the power converters, most of the charging circuits are lies inside your vehicle. Okay. On the other side, in the off-board charging scheme, most of the charging circuits like DC AC or AC DC converters are lies outside the vehicle. So both are having their advantages and limitations. So like if we talk about the mode 1, that is the slow charging, on-board charging. So this technology refers to home charging. So you just simply take the supply from your outlet at your home and charge your EV. Okay, this type of charging involves plugging an electric vehicle into standard household sockets. Okay, just you take the supply that is coming to 20 to 30 volt from your socket and charge your system, charge your EV. This method of charging does not provide users with shock protection against DC currents. So there is no any scheme of protection at that this type of charging. So if you see this figure, AC-DC converter and the DC-DC converter is lies inside the vehicle, which make it on board. So on the one side, you are having all its circuitry inside the vehicle, which make it more compact and efficient. On the other side, it is a slow charging scheme. Basically, you cannot able to charge it very fast. Okay. We will discuss in the coming slides about that one. So there is another mode of charging, mode 2 charging. It is also the slow charging scheme, but is having some protection features. So it involves the use of special cable with integrated stock protection against AC and DC currents. Okay, so it is having some scheme for that one. Unlike mode 1 charging, mode 2 charging cables have built-in protection in the cables which protects against the electrical shock. So it is this mode 2 charging is the most common mode of charging right now. Okay, so mode 2 charging is the most common one to charge your electric vehicle. The mode 3 and 4 are called the fast charging scheme or DC fast charging scheme. Okay, or fast charging. So in somewhere, ultra fast charging scheme is also coming into the picture as a mode 4. Okay, so the widely varying charging rates for mode 3 and mode 4, that is 5 kilowatt unit to 50 kilowatt and 150 kilowatt plus the soon to be rolled out 350 and 400 kilowatt standards. So it's in the process to make the standards for all this charge. There is no any fixed standards. Number of standards are coming like Indian standards, or you can say the international standards for charging scheme, but it is in process to finalize all these standards for the EV charging. So in concise form, if you define the level of charging, so how could you identify the level of charging? It depending on the voltage level and the power level. So for the level 1, the power ranges from 1.4 kilowatt to 2 kilowatt and supply of having 120 volt. For the level 2, it is 3.3 to 22 kilowatt. That could be up to the 30 kilowatt for the light electric vehicle. And the supply is the 240 volt AC. On the other side, the DC fast charging or the ultra fast charging, the power level is in between 50 kilowatt to 600 or 700 kilowatt. Okay. Particularly for the ultra fast charging, we always prefer power greater than 350 or 400 kilowatt. For level 1 charging, the charging time is 8 to 20 hours, and for level 2 is 3 to 8 hours, level 3 20 to 60 seconds, and for the ultra fast charging it is 10 to 20 minutes, and for level 3 that is 20 to 60 minutes. That is the difference. So there, you can see there is a huge difference between the level 1 charging and the level 3 charging. Level 1 charging taking 8 to 20 hours for full charge of your battery for the same rating. On the other side, level 3 charging is just taking 20 to 60 minutes to charge the same power rating of ampere hour rating of the battery. So if you want to charge your battery fast, you must go for the level 3 charging. However, it needs a special infra circuit or arrangement for the fast charging of your EV. So this is the mode 1 to mode 4 charging scheme. In the mode 1, there is no protection scheme is there, no fault scheme is there. However, apart from except mode 1, all the modes are having fault and protection schemes are there. So these are basically 4 mode of charging of your electric vehicle. So there are number of configurations for your charging schemes for level 1, level 2 DC fast chargings, and people are doing a lot of work using different converter schemes and different arrangements to make the charging scheme effective and efficient, and your powertrain more effective in all modes of operation. So there are basically 3 modes of operation are there in the electric vehicle. One is the plug-in charging, the second one is the propulsion, and the third one is the regenerative braking charging. So in the conventional systems, for all these 3 modes, we need 3 different DC-DC converters, or at least 2 DC-DC converters. Okay, but in the recent research and what we have developed in our laboratory, like this topology, I am going to discuss is developed by our team. In such a scheme, with just using a single unit of power or DC-DC converter to take care of all these modes: plug-in charging, propulsion, regenerative, with the grids and the solar supply with the battery. Okay. So it is the example of one of the such scheme we have developed, we have proposed. So you can see in this scheme, a single unit of integrated converter. A single unit of integrated converter is take care of all the possible modes in this EV. This EV is of having BLDC motor. Okay. So you can see the solar power source is there, the grid is there, and the battery is connected here. Okay. So the special feature of this particular proposed integrated DC-DC converter, it is basically the modified canonical switching cell converter. This converter is derived from the canonical switching CSC converter. CSC converter is nothing but one of the type of buck boost type of converter. Okay, but having inductor at the input side. Okay, so like if solar is used to charge the battery in the charging scheme, in the resting condition of the resting mode of the motor, if you charge your battery, EV battery, with the solar, this converter is acting like a maximum power point tracking converter. Okay, and optimize the PV panel output power at all insolation levels or all environmental conditions. On the other side, if solar power is not available or battery is charging through the grid, the same integrated converter will act like a PFC converter, power factor correction converter, and taking care of the power quality at the grid side. Similarly, in the propulsion mode, in the regenerative mode also, the same unit of DC-DC converter is used to driving the motor or in the regenerative operation. So by just eliminating the 2 more DC-DC converters for the solar PV system or for the PFC converter, we just proposed a new single unit of integrated DC-DC converter to achieve all these operations. Okay, so like in the plug-in charging mode, if you charge your battery, EV battery using the grid, you can see this converter is act like a buck boost converter. Okay, this converter is also having a feature of both a step up or step down the input voltage. So in the plug-in charging, you just take the supply from the grid. This converter is acting like a power PFC converter, power factor correction converter, and operated the grid at the unity power factor, UPF. Okay. On the other side, if you charge the battery, EV battery with the solar, if you charge your EV through the solar, then the same unit of converter is acting like an MPPT, maximum power point tracking converter. So you don't need any additional DC-DC converter at the solar side to optimize the performance of solar panel at different environmental conditions. Okay, you just apply, you just using the switch SA as a boost converter switch and optimize your solar panel output power by implementing P&O, INC, or any type of MPPT technique, control technique. Okay. On the other side, in the propulsion, in the running mode of the electric vehicle, the same converter is act like a boost converter. And in that case, the switch SA and SE are off, and the switch SB comes into the action, and it's act like a boost converter. And the diode of this switch SC is acting a diode, output diode of the boost converter in the propulsion mode. So you can see at a time, only one switch is working in both the charging mode and in the propulsion mode. And in the regenerative braking mode, both the switch SA and SCR comes into the action. Okay, and it's act like a bidirectional buck boost type of converter. So in this case, both SC and SA comes into the action and charge the battery through the regenerative braking. So you can see, you can observe the same unit of converter is operating or having in all type of modes of electric vehicle. So there is a compactness, it's result into the compactness of the system, it results into the high efficiency of the system. So there are a lot of advantages of using this a single unit of converter. This is the control technique implemented in this system. So there is a torque braking command is there, and depending upon this torque braking command, it is selected whether there is a propulsion mode or there is a regenerative mode is there. A very simple control technique is there. And there is the control technique at the BLDC motor side. We have also integrated or incorporated the soft starting technique in the BLDC motor by just taking care of the duty cycle of this PWM technique. Okay, and using the Hall effect sensors commands. So in the regenerative braking mode, particularly we just maintain the DC link voltage, and it would be somehow plus minus 5 volt, less than or greater than 5 volt for the better operation, particularly in the regenerative mode of operation. So this whole control is about the control or effective control of the BLDC motor. So you can see this is the winding current of the BLDC motor. There is a sudden increase or decrease in the motor winding current in the regenerative operation or propulsion mode or the regenerative operation again. So we have very careful about to design the controller at the motor side by taking care that there could be no any sudden increase or dip in the motor current across the windings in the throughout the driving cycle of its operation. So there should be very careful in defining or designing the control at the motor side. These are some experimental results. We have also implemented in develop a hardware setup and tested it there. So you can see there is a unity UPF operation is there. The TSD is less than 4%. So it's will follow the IEEE 519 rule that say that it should be the TSD in the current and voltage should be less than 5% or in some cases 6 to 7%, less than. These are the converter performance. You can see this channel 4, the current through the inductor, and this is the current through the inductor L1, and this is the current through the inductor. In both the cases, we operated this converter in the CCM mode, continuous current mode. So there are a lot of advantages to operate the inductor in the CCM mode as compared to the DCM mode. Okay, there is a less stress and other advantages are there. There is less AMI problem if you operate your inductor or the capacitor in the CCM mode as compared to the DCM mode. Okay, uh, the this figure shows the performance of the system under the different solar insolation level. So even though at the change in insolation level from 600 to 1000 and 1000 to 600, there is a smooth tracking of solar PV output voltage, panel voltage, or you can say MPPT voltage. So there is no change in the MPPT voltage, which demonstrate or authenticate the effective MPPT control is implemented and working well in the control tech. So these are the motor parameters performance in the regenerative and the propulsion mode. You can see we have achieved the efficiency more than 94% at 1 kilowatt per. And you can also observe from this figure, if you increase the power rating, if you scale up this system, you can achieve more and more efficiency. Okay, so it is also one of the characteristic of the proposed system. On the other side, if you compare the cost of the conventional system and this proposed system, there is a huge difference. Like for the conventional, it is $241.2 is there to design such system. For our system, it is $176.6 is just needed. Okay, so there is also cost effectiveness of the proposed, because we have drastically reduced the number of components on the solar side, on the motor side, on the grid side. So whatever the system we have discussed is about the unidirectional. There is having no capability of vehicle to grid operation is there. So in some cases, we also need to supply power from your vehicle to the grid. Okay, so for that one, we have also designed such system for that one, like single phase grid is there. This is the bidirectional, you can say controlled rectifier using the IGBT switch. And this is the Zeta converter. So we have proposed this system, or we designed a system for having both vehicle to grid and grid to vehicle capability. So this is the converter is switched capacitor bidirectional high gain Zeta converter. Okay, and this is the solar panel directly connected to the terminal of the battery through the CUC converter. So there is a number of possibilities in this configurations. So you can replace this CUC converter by the buck boost type of any buck boost type of converter like Zeta, SEPIC, or simple boost of buck converter, or you can directly connect this solar terminal at the battery side and to make the system single stage. For that one, you need to control the current through this converter, or to achieve the MPPT performance of the solar panel through this converter. So there could be one possibility to eliminate this converter too in this system. Okay. However, by using this buck boost type of like CUC converter at the solar side, there it provides the flexibility to use the different ratings of solar panel, because it is having both the capability to step up or step down the voltage at the input side. Okay, so if the solar power rating is greater than the battery voltage rating, then it step down. Or if the solar power is a voltage output is less than as compared to the battery terminal voltage, then it will act like a boost converter. So it is beneficial to use the buck boost type of converter there. So if this converter operates in grid to vehicle, the simple Zeta operation is there with the switch capacitor. So these are the some A and B are the modes for charging and discharging in the grid to vehicle mode. On the other side, when this operate at a vehicle to grid mode, then again it's act like a Zeta converter. Okay. And a simple solar PV charging mode, a solar PV is there, a CUC converter is there. So it is a very simple circuit. Solar is charging the battery through the CUC converter. A CUC converter is used, a SEPIC or CUC converter is used with the solar, is having some advantages over the simple buck boost converter, because if you use the buck boost converter, no doubt it has the less component as compared to the CUC or SEPIC converter, but the stress on its components is very high as compared to SEPIC, CUC or Zeta converter. So it's always prefer to use SEPIC or JITA or CUC converter. Among all this, the CUC converter is one more advantage, that it is having inductor at both sides, both the input side and the output side. So what I recommend always, to use the converter that is having inductor at the input side with the solar. Why? Because if there is a 1 or 2% ripple, like just let's assume there is a 6% of ripple in the current at the output of this PV panel, it will lead to the 2 to 3% power loss reduction output of the solar panel. Okay, so it's always prefer to use such converter that is having the input inductor with the solar system, so that you can further optimize the performance of the solar panel output. Okay, so in this such structure, CUC is preferred over the JITA one. So this is the control logic here for the power quality improvement or to taking care of the grid supply. IMS TOGE, it is simple, the third order generalized integrator with the multi-layer system. Okay, so this control technique is taking care of all the possible conditions for the power quality, like sag, swell, DC offset, taking care of all these conditions. So it is very effective control technique at the grid side we have implemented there. And this is for the converter. This is for the proposed switched capacitor high gain JITA converter. So this converter is basically derived from the JITA converter, make it high gain and switched capacitor for both grid to vehicle and for vehicle to grid operation. Because if you are having a system with both vehicle to grid and grid to vehicle operation, you always need a high gain converter. Because likewise for the grid side, you need 230 volt or something 300 volt or 200 volt DC. So from the battery from 48 volt to step up from that voltage level, you always need a high gain converter. So it's always prefer to use high gain converter in such system to achieve the G2V or V2G operation, or even vehicle to vehicle operation, V2V operation. So these are some simulated result for this system. So you can see there is a unity UPF operation is there in the charging mode. And this is the performance of the system under varying insulation level. There is a smooth MPPT tracking is there. There is no change of MPPT voltage and a sudden change in insulation level. And this increased SOC showing that the battery is charging continuously through the solar power. This is the motor side performance. That is the line to line voltage. This is stator current, motor winding current is there. The speed is constant throughout the operation. And these are some experimental results are there which will validate the simulated results. So now, apart from these two configurations, I am going to discuss a very interesting configuration of N-phase SRM drive system. Like basically we are using special machines for the electric vehicle like PMSM, BLDC, or SRM. For light electric vehicle, we always prefer to use the BLDC motor, and for the heavy duty electric vehicles, we prefer switch reluctance motor or the PMSM. Why? Because in the BLDC motor, there is a problem of the torque ripple is there. Okay. However, in the case of SRM, in the case of PMSM, there is a less problem exists like the torque ripple or the noise. Even though in the SRM, there is a problem of torque ripple as compared to the PMSM, but if there are number of methods are there to compensate this torque ripple problem or the noise problem in the switch reluctance motor. And along with that, a numerous advantage of switch reluctance motors are there over this BLDC or PMSM. The first one is that it is free from rare earth magnet. The switch reluctance motor is free from rare earth magnet. So you are not, we don't need to depend on the countries like China that is having the monopoly for the rare earth magnets to manufacturing this type of PMSM or the BLDC motors. Okay. We just need a two-piece of iron. Okay. We just need a two-piece of iron to make the switch reluctance motor. Nothing else. So it is very cost-effective to design to manufacture the switch reluctance motor. Along with that, as compared to the BLDC or the PMSM motor, it is self-tolerant structure because all of its windings are separated or magnetically or electrically separated with each other. There is no dependency of one winding to on the other. And we just need 4 to 6 switch of converters to run the switch reluctance motor in the propulsion mode, particularly in the case of EV. So here we are going to discuss a compact solar assistance on-board charging scheme for N phase. For N phase, it is the universal one. You can take the 4-phase, 6-phase, 8-phase, 12-phase SRM. It is applicable to all, just using the asymmetric hybrid half bridge converter. Okay. So this is the proposed system. On-board charging system is there. We just take the charging from grid supply or the DC supply or the AC supply through this converter. So in the last two topologies or configurations, we have seen that the DC-DC converters are required for charging the system or to overcome or you supervise the power quality at the grid side. But there is another scheme. There is another scheme of charging the battery or in the propulsion mode, running the motor. It itself use the winding of the motor to make it the converter configurations. Okay, so just by taking the inverter of the motor and the windings of the machine as an inductor to configure different type of DC-DC converters. So you don't need any extra DC-DC converter in the system. Okay, so it is also one of the concept to define or you can design the charging scheme for the EV system. So in the proposed system, integrated converter N-phase SRM drive with the same number of power electronic switches. We don't need any extra DC-DC converter or any extra switches to design the charging scheme. Same inverter and the same motor is used to configure the different power electronic converters to charging the system. During propulsion, this proposed integrated converter is reconfigured an N-phase asymmetric half-bridge converter. And for the batteries charging, 2 relays or contactors are used to configure. So this is the structure for proposed asymmetric half-bridge converter for the N-phase SRM. We just need 2 contactors or 2 relays J1 and J2 to reconfigure this proposed structure into different form in the different modes of the charging scheme. Okay, so this is the proposed system. Like if you want to charge your system in the single phase supply, if you are having the single phase supply and you charge your system, just make the connection like this. Connect the 2 supply, positive and negative here, to phase A and phase C and close the relay J2 and open the J1. So you can see it will come into this form. 2-stage battery charging system. The first stage is bridgeless boost converter and the second stage is bidirectional DC-DC converter. And you can have charged your battery by using the same converter. So if you are having the single phase supply, this converter reconfigure as a bridgeless DC-DC converter and in the second stage bidirectional DC-DC converter. Similarly, if we are having the 3-phase charging scheme, in this case, this converter, this proposed converter is reconfigured is like this. The first stage is 3-phase boost converter and the second stage is the bidirectional DC-DC converter to charge the battery. In this case, J1 is closed and J2 will open. So by just using these 2 contactors, these 2 relays, we can reconfigure this proposed scheme for the single phase charging, 3-phase charging, DC charging, vehicle to vehicle charging. Like if we have solar battery charging, if we have the solar and to charge the battery, just open the J1 and close the J2 and make this connection like this. We have a dual active bridge converter by using the same asymmetric high bridge converter and charge your battery using the solar system by the DC system. So it is the beauty of this proposed converter. And this is the flow chart to select the mode, whether it is in the driving mode or whether it is in the charging mode. So these are some results we can see in the single phase charging or in the 3-phase charging. We achieved the perfect result. At unity power factor operation, battery is charging successfully. One thing that should be taken to the mind, throughout this charging, whether it is the single phase or the three phase or the DC solar charging, the average torque should be zero. So we must be very careful about that one also, that there is no rotation in the rotor. Okay, so thank you for that one. I am closing here my presentation. Hi, Jatin sir.
Thank you so very much, Anjanee
Yeah.
sir, for such a fruitful session on
Yeah.
different EVs
Thank you,
and
sir.
configurations
Yeah.
and various power converters. So thanks a lot, sir, for enlightening us with such fruitful results. Now, we do have some sir questions from our
Yeah.
participants.
Please.
Just give me a moment, sir. So, sir, first question is from Beamsin to do. So, the question is, what are the current advancements in solid-state battery technology, and how soon we can expect large-scale commercialization in EVs?
Yeah, likewise, apart from the lead acid and the lithium ion batteries, sodium-based batteries are also comes into the action. But we have to wait for more 5 to 6 years to come into the commercialization of this one. Right now, lead acid battery and lithium ion batteries are mostly used.
Okay, so, sir, our second question is from Vijetha Kilamasetti. So, question is, what could be the impact on efficiency if only the electric motor or only the engine is used in the system?
Uh, like what we put it in the literature, if you carefully select the motor and its control technique, there could be the 20 to 30% of efficiency improvement. There is a change of 20 to 30%. So the role of motor and its operation in its, particularly in the driving mode, it's very much important because it affect 20 to 30% of efficiency, overall efficiency of the EV. Both, if we consider both the driving and the regenerative operation. So we always select the motor very carefully for our EV.
Okay, so some next question is from Srinivasan.
Yeah.
What is CAD-demo charging system and is it available in India?
Yeah, right now it is somewhere like it is one of the standardization standard to use for the charging system. But right now, like if we take the example of Tesla charging, there is no any standard following by the Tesla, so it is under the process. So there are different charging, Bharat charging, BIS, and different charging standards are there, but all are in process to finalize and meeting the international standards.
One more question is there, sir, from Prashant Rajput. What are the primary objectives of advanced control and optimization for EV powertrains?
Repeat it. What?
The question is, what are the primary objectives of advanced control and optimization for EV powertrains?
Yeah, likewise, it is very important to design your powertrain system, particularly in the case of regenerative braking. If you take power from the motor in the regenerative case, it would enhance your charging capacity or your efficiency of your system by 10 to 12%, 10 to 15% even, if you carefully design your regenerative operation. So the design of powertrain, if you include the DC-DC converter and the regenerative braking operation, so it would very much having the effect on the efficiency and the optimization of the performance of the EV. So it's always prefer to design very carefully the regenerative operation as well as the selection of the DC-DC converter. And that's why we have discussed how we can able to reduce the number of components on the DC-DC converter. In all 3 or 4 modes, I have discussed that there is always a possibility to reduce the number of components and maximize the modes of your operation. Okay, so by a single unit of converter, even though you can reduce in that converter the number of components, you could be able to achieve more and more compactness and efficiency. So it's always preferred to design very carefully your powertrain and the optimization technique for you, such that like for the battery management system, even also optimization is very important. Like if you take the example of supercapacitor, so what we have discussed, along with there is a series connection of supercapacitor, there is a need of balancing across the supercapacitor voltage. So we have discussed that it's, even though improve the dynamic performance and the transient performance of EV, there is limitation of having balancing across the all these supercapacitor units. So it's always need to design very carefully the balancing of this supercapacitor voltage across the supercapacitor voltage. So there is a huge, you can say, the scope of research at all the parts of the EV, starting from the grid to the motor side.
Yes, sir. And we do have one more question from
Yeah.
Gayatri. Sir, what are the different control algorithms commonly used nowadays?
Like at the motor side, there are number of control techniques are adopted and utilized in the DC-DC converter sides are also, like if we take the example of DC-DC converter side, digital control are also used along with the other control techniques are there. They are having their own advantages. On the motor side, like there is two type of control techniques are there. If you take the example of BLDC and switch reluctance motor, one technique is the fundamental switching technique. Fundamental switching technique means you just switch your converter at the 50 hertz, maximum up to 100 hertz. So, okay, and we all knows that the losses across the switches is directly proportional to the switching square of the switching frequency. Power is directly proportional. Power loss is directly proportional to the square of the switching frequency. So in the fundamental switching operation, that could be possible, particularly in the case of PMSM and BLDC motor, you can able to save your energy in the switching process. On the other side, if you do for SPWM or SBM or high frequency switching at the motor side, there could be some protection enhancement. Along with that, there could be increase in the switching losses. So there is a trade-off between all these things. In the like in the fundamental switching, that in the technique of the, that is also called the electronic commuted technique, you can also able to reduce the number of sensors. There is no need of any current or voltage sensors at the motor side. But in the high frequency switching of the converter at the motor side, you need at least two voltage or two current sensors. Even though one current or one voltage sensor is there, like one concept of control technique at the motor side adopted is like current reconstruction. So just by taking the DC current, or you can say the current that is coming to the DC at the output of the inverter, you can reconstruct all the three phases current of the PMSM or the induction motor. So there could be a number of possibilities of the control techniques design at both the converter side DC-DC or at the motor side, even though at the grid side also. You can use the PLL technique, you can use the PLL-less technique like SOGI, second order generalized integrator, third order. So there could be number of possibilities to develop the control techniques either at the grid side, converter side, or the motor side.
And sir, one question is from Satyajit Sahu.
Yeah.
I think we are having a lot of questions.
No problem, no problem. I am enjoying, please.
So, yeah, one question is from Satyajit Sahu. Can we use standalone power station for on-the-go charging in EV for emergency cases? And what about charging the vehicle while on the go? Is it harmful or any limitations?
Standalone charging?
Can we use standalone power station for on-the-go charging in EV for emergency cases? And what about charging the vehicle while on the go? Is it harmful or any limitation?
Yeah, what I am understanding from the question that it is not possible to charge the battery in the running case. It's always possible when the rest mode, the vehicle is in the rest mode. And about the standalone charging station means like solar based charging system, or I don't understand the question. So
okay, sir, in this case I think we shall give permission to the participants.
Yeah,
because
please.
Gayatri is having some more questions, so I think we will have to give permission to them.
Please.
Yeah, sure, sir.
Yeah.
Sony sir, can you I'm making her contributor, Satyajit Sahu.
Yeah.
Okay, Satyajit, you can ask the question and turn on your mic and ask the question.
Please, Satyajit.
Thank you, sir, for giving me the opportunity.
Yeah, please.
Actually, I am talking about the power station that are like small, having a small power backup with it. We can buy them some. I saw a link. One of my friends forwarded me the link on Amazon,
Yeah.
where we can use the standalone power station, which are very compact in nature, maybe 3 kg and compact nature, which can power up to maybe small EVs or bikes, or maybe small scooties which have this facility. So I was asking whether it will be safe to carry these power stations and maybe charge if we are already running low on battery on the go, like while we are driving. But I guess you are telling that while we are running, we should not charge the vehicle.
Yeah, that is one of the thing. And what I'm understanding from that one, it is just similar to the case of like vehicle to vehicle charging. Just if you carry the standalone power station like that one, it's also carry the battery, I think. Storage power is there, na?
Yes, sir. Yes, sir.
Yeah,
Yes,
so
sir.
it
You
is
can.
just yeah, so you can charge it. There is no problem. There is another concept of battery swapping is there. You can just replace your battery from the vehicle and put it the another battery is there. Or in the standalone power, you can charge it. There is no problem there. Like in the vehicle to vehicle charging, V2V charging, we perform the same action.
No, sir. My question is, while driving, we should charge it or not?
No,
Like,
how it, no,
like
I don't understand how it could be possible that at the same time battery is discharging and the battery is charging.
sir, it might be very silly, sir. But while using the mobile phone, we are also able to charge and use it, sir.
Charge
So
at a
yes,
time,
while
same time.
yes, like our handphones, sir, our mobile phones, we are able to charge it and simultaneously use it as well, sir.
But it is, yeah, it is, but not in practice in the EV. So I might be not aware of that.
No, it's just like all the after all the presentation I saw. So this can also be one of the possibilities, like on the go charging or so might be we can have some research on it, and we can, because it is not like the main point I want to ask is whether it is harmful or not. Like charging the vehicle and simultaneously using it, it
Same
might be
battery,
harmful.
same battery.
Same battery, sir. Same battery.
Okay, okay. So we will see that one. It is also maybe one of the point of research is there.
I will share the link of the power station I was
Please,
talking to in
please,
the
please.
WhatsApp group. So
Yeah,
might be you
please,
can have
please,
the idea, sir.
please, please, please.
Thank you, sir.
Thank you.
Okay, so Balaji, AP, Triple MVIT, please turn on your mic and you can ask your question.
Sir, good evening, sir.
Good evening, sir.
Sir, actually, I'm doing research in EV, sir.
Yeah.
My research topic objective is to optimize the electric vehicle efficiency, sir.
Okay.
I don't know where I can start my work regarding the base paper. So, can you suggest some base paper to get a clear cut idea for doing the research?
So, Balaji, there are two things are there. One thing, I frankly speaking, what is your guide area? You must focus on that one, the first thing.
Okay,
So
sir.
that would much beneficial for that one. The another thing is that there is a
Okay.
number of possibilities, starting from the charging to the propulsion to the regenerative. So if you are interested to do the work in the DC-DC converter, I must suggest
Okay.
you must suggest to work on the onboard charging scheme.
Okay, sir.
Use number of possibilities of using the multi-level converter, multi-phase dual active bridge converters, isolated high gain converters. On the other side,
Okay.
on the other side, if you are having interest in the motor control, then the motors like the synchronous reluctance, SYRM, switch
Yes,
reluctance
sir.
motors, PMSM
Yes,
motor
sir.
are there, and the number of possibility to design the control techniques with reduced sensors, with another switching techniques, efficient switching techniques are there. So
Yes.
these are the some, and by all the way you can able to optimize your EV efficiency.
Okay, sir.
On the
Sir,
other side, yeah.
for this, can you suggest some base paper? This, if you want to refer this particular paper, you can get some ideas so that I can ask. Sir.
Uh,
If
yeah,
possible, you can share the paper link in a WhatsApp group.
yeah, so yeah, sure. I will share it.
Okay.
Yeah, I will share it.
Okay, so next question is from
Thank you,
Artik
sir.
Karthik.
Thank you.
Next question is from Arthi Karthik. So please turn on your mic and you can ask your question.
Hello, sir. Myself, Aarti.
Yeah.
Hello, sir.
Hello.
So I'm doing my research on solar power vehicle. I'm in the starting stage.
Okay.
We have designed a vehicle in our campus such that it is running only on
I'm sorry to
battery.
interrupt you in between, Anjanee sir. Can you please turn on your cameras so that our participants can be well aware?
Yeah.
That will be sort of,
Yeah.
Yeah, thanks, sir.
Yeah.
So,
I recently got an accident in my left hand. So
Because last time when I saw you, we were in Thapar at that
yeah.
time. I was
Yeah.
your student, I still remember.
That's yeah.
hello, sir.
Okay, so yeah, Aarti, please continue.
Sir, we have designed an rickshaw type of vehicle in our campus. Now we are planning for a solar panel to be installed on the rooftop, sir. How to select the solar panel regarding the rating, whether it has to be higher than the battery rating or it has to be less than the battery rating? I don't know
Yeah,
that.
for that one, we have discussed that the buck boost type of converter. And I always prefer and I always suggest to use such converter that is having inductor at the input side with the solar system. Okay. And the buck boost type of converter like Jita, Kirk, Sapic. Okay. So if you select that type of converter with your solar system, it would be very beneficial so that you can having the flexibility to change your solar panels. Okay.
Okay.
Because it's always preferred to use like in the e-rickshaw because what is the unit of insolation like 1000 watt per meter square. What it's mean that 1 meter square of having area 1000 watt. Okay, solar panel is giving 1000 watt for 1 meter square. And what is the efficiency of the solar panel? That is 20% maximum. What it means that if you buy a 1000 watt solar panel, it will give you 200 watt per meter square at the maximum insolation. This is the standard conditions. So for 1 meter square, you can get the 200 watt. Okay. So if you having the electric vehicle of 750 watt motor rating, you must need of more than 600 watt of solar panel. So you must need an area of more than 3 meters square. So it's always recommended to select your converter and your system very carefully because we have a very limited space on the vehicle. Because in the running mode, it will just come into the idle load. Okay. So what I'm suggest if you are new in the solar vehicle system and you want to do that research on the solar vehicle, do it on the DC-DC converter and particularly partial setting conditions. The optimization techniques for the partial setting MPPT control techniques. There is a huge scope in that one.
Okay. Thank you, sir. Thank you so much.
Yeah, because when the vehicle is running, the case of partial setting is very often. So if you develop a control techniques in the partial setting conditions, that would be very interesting for your research.
Thank you, sir. Thank you so much.
Yeah.
And now, sir, this is the last question from Gayatri Devi.
Okay.
So, Gayatri, please turn on your mic and please ask the question.
Thank you. Sir, good evening, sir. Myself, Gayatri.
Good evening, Gayatri.
Sir, actually, I'm doing research on electric vehicles, sir. And mainly, I am in motor side only, I am concentrating, sir. In BLDC motor, I am trying to control the speed and torque.
Okay.
Of different conditions of the road. And for that, I am using some AI optimization techniques, sir.
Okay, perfect.
As you said, in that motor control side, you told that direct switching method means that direct torque control only you are telling us, sir. DTC and VOC, vector oriented control, and direct torque control.
No. For the motors like switch reluctance motor and BLDC, DTC or vector control would be not much effective. Okay, DTC and vector control, FOC control, field oriented control are most suited to the PMSM drive or the induction motor drive that is having the sinusoidal back EMF. Okay, the BLDC motor or the switch reluctance motor of irregular shape of the current and the back EMF, not directly the DTC. I am talking about the fundamental switching techniques. Electronic commutation technique is there. Okay, just like if you take example of BLDC, just switch on the one winding and switch off all three windings or two windings, then switch to the second winding. switch off the first or third. So electronic commutation is basically the process to generate a rotating torque in the BLDC or switch reluctance motor with a very less operating frequency. Okay, so what I suggest to not directly use the DTC or any FOC control techniques. There are very simpler techniques, control techniques for the DTC, for the BLDC, and for the SRM are there. Particularly in the case of BLDC, it is very simple to use a very Hall sensor based techniques are there, switching techniques are there. Just take the 3 Hall sensor signals and try fundamental switching techniques. Don't sense anything and do the fundamental switching at the converter side and control the DC link voltage from the input side. Why you go for such complex control technique for the BLDC one? It doesn't need that one. Okay.
Okay, no, actually, I am in the starting stage only, sir. So
Yeah.
whenever I am doing the literature reviews, I am seeing that one only. DTC and FOC only I am commonly seeing. So I thought for our BLDC also I can use those techniques.
There is
And
one book.
AI
Yeah, there is one book, R. Ramakrishnan and Jan Boldia. 2 books are there for the BLDC.
Sir, can you please tell again, sir? I will not.
R. Ramakrishnan.
Okay.
One, yeah, and second one is Jan, IAN, Jan Boldia.
Yeah.
Okay.
Okay.
Number of control techniques are there for BLDC and SRM. It would definitely help you.
Sir, that BLDC itself I can use, sir, or otherwise I have to go for PMSM, sir?
BLDC, no, if you're targeting for the electric vehicle, light electric vehicles like e-rickshaw, e-bike, then BLDC would be the best one.
Okay.
And for the PMSM, that is for the heavy duty cycle. The one advantage of having with the PMSM is that all the control techniques of the induction motor can directly be implemented to the PMSM motor. So 2 ways are there. Like because there are huge number of control techniques for the induction motor, you can directly use that control techniques for the PMSM. And PMSM is having the sinusoidal back EMF for your current. So it is always used simpler to design that control techniques for PMSM. But it is costly. It is 3 to 4 times costly as compared to the BLDC. Like if you go for the market and buy 1 kilowatt of BLDC, it would have 20,000 or 19,000 and PMSM of 93 to 95,000 rupees. 3 to 4 times more than cost.
Okay, so you're telling that V-bar of everything we can use for PMSM, sir?
Yeah, everything for PMSM. All the control techniques are as it is implemented into the PMSM.
Okay, so this BLDC also fine only, sir, or I have to change because you are telling this much.
No, very perfect motor. I always prefer to use BLDC one.
Okay.
Yeah, because for the PMSM, a high resolver is needed. That is a very costly resolver because you need position. You need the rotor position at every point. But for the BLDC and SRM, just take a 3 Hall sensor of 75 rupees. You can develop your hardware.
Okay.
Both are very good motors. It's depend on you.
Sir, that AI optimization means that I am using one PID controller. With that, for increasing the efficiency, I am using some optimization techniques. In that only, I am asking that control algorithm, sir. Mainly that MPPT tracking and all previously during my PG time and all, I have used that ANFIS technique only. So according to my guide, what he is telling that is outdated only. You have to go for some new techniques.
Which one is outdated one?
That ANFIS, adaptive neurophysics.
No, not a lot of works are doing modified one and that one. So none of the research is outdated one.
Okay, that current trends, if anything is there, means can you tell? Means it will be very helpful, sir. That's it.
For what?
That optimization technique like this ANFIS, fuzzy was there, then ANFIS like that Jaya algorithm something,
that can be used at the solar side, and like the LMS least mean square, LMS adaptive LMS, lot of techniques at the motor side you can be applied.
Okay, you're telling about machine learning, yes, sir. Then
yeah, machine learning techniques are there. AI techniques are there. Okay.
Okay.
Yeah, but
Okay, sir. Thank you, sir. Thank you
okay,
so much, sir.
okay,
Please share your contact details also, sir.
okay, okay. Sure, 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 sure.
Thank
Okay,
you.
so sir, this is the last question from Aarti. Sorry,
Yeah,
sir.
yeah. No problem.
Sorry for this.
No
So this is
problem. No
last
problem.
question from
There are a
Aarti.
lot of questions today.
Yeah.
There are a lot of questions actually.
Yeah, no problem.
Sorry, sir, to disturb you again.
Yeah, yeah,
No,
please, please.
no.
Sir, in the point of in the data set collections regarding a battery powered vehicle or a solar powered vehicle, is there any websites, particular websites are there, sir?
Actually, I don't know about that one. I am not working on that one, data analysis and all these things.
Okay, sir.
So I could be not able to suggest such sites.
Okay, sir. Thank you, sir. Thank you, sir.
Yeah, thank you.
Okay, so thank you so much, Anjanee sir, for such a fruitful session. Really, it was very interesting. We were having a lot of questions, obviously.
No
So
problem,
because
sir.
half an hour to 45 minutes were,
Yeah, yeah,
focusing on
sir.
questions only. It was really good, sir.
Yeah. Thank you so much, Jatin sir and Akashdeep sir,
Thank
for
you.
giving such a wonderful opportunity to talk with you all and share whatever I have limited knowledge.
Sir, thanks a lot, sir. So we are your students, sir. We have
No,
learned
no.
a lot from you.
Yeah.
So, yeah. Okay, sir. Please share your presentation, sir, and we will
Yeah,
share your
yeah,
contact
yeah, yeah. Today only.
We will share it with the participants also.
participants, and we will
Today
share
only.
your
Within hour, I will share. I will
and
share.
we will share your contact details also, sir, with the participants in case
Yeah,
some
yeah.
future collaborations are there.
Mail ID, contact detail, and
Yeah.
bring in.
Thank you,
Thank
sir.
you
Thank
so
you so
much.
much.
Thank you so much
Thank you, sir.
Thank
Thank
you.
you.
to all.
So thank you so much, all of you. We will start the next session from tomorrow onwards. So thank you so much, and good night. Thank you.